Hello everyone, my name is Shenaj and I will present our work titled K-Merge, or Continual Merging of Adapters for On-Device Large Language Models. Low-rank adaptation, or LoRa, is a parameter-efficient fine-tuning method widely used for LLMs. Given an LLM with weight W0, we keep the model frozen and instead fine-tune two low-rank matrices, A and B. The output is computed as if the weights were W0 plus B times A. This allows us to train many LoRa's very efficiently, a single shared base model with one LoRa per task. For instance, one for smart reply, one for summarization, and so on. These are the tasks we consider in this work. So what's the drawback? Potentially we have n task adapters, one per task. We could combine them into a single model. Many approaches exist for this, such as linear merge, their ties, and so on. But to do that, we will need all these adapters to coexist at the same time, and by merging them all into one, we might be wasting available capacity. What if we keep K adapters instead? We propose therefore the new setting of online continual merging of adapters. New LoRa's are downloaded from the web over time as new functionalities become available. Each LoRa adds a new task, and tasks are cumulative. We want to merge LoRa's as soon as they arrive. Typically there is no room to store all of them, and we assume a storage budget K, much smaller than the full sequence of LoRa's. We propose a new method, with two variants designed for this setting, K-Merge and K-Merge++. In the example shown, we consider a storage budget K equal to 4 with no initial adapters. When a slot is empty, we store the incoming LoRa in an empty space, and repeat it until all slots are full. Each time we store a LoRa, we record where it went in a merge history metadata age. In K-Merge++, the decision is adaptive, based on a threshold that has been tuned on a held-out validation set of completely different task language combinations. When a new LoRa arrives, we compare it to the stored ones. If the cosine similarity is below the threshold, we start a new cluster. If it's above, the new LoRa is merged with the closest cluster, and we update the cluster merge history. Once the storage budget is full, the only remaining option for both the strategies is to select which LoRa to merge. We compute the argmax of the similarity between the incoming LoRa and the existing ones, and merge it with the closest one. Here we show the selection and merging in a cosine similarity space. We treat each LoRa as a vector. We project the incoming model, find the closest by cosine similarity, and merge them. The merge rule is a running mean that accounts for the history of merges, shown here. In practice, the similarity is computed on the flattened LoRa's and averaged over layers and projections. To evaluate our approach, we consider a set of 40 LoRa's, 5 problem types, and 8 languages. Each LoRa is trained on one task, a problem type in alpha in a specific language in beta. As time passes, we download and merge each incoming LoRa, and the model grows in capability. Evaluation isn't trivial. At each step, we test on all tasks seen so far. So we ask a simple question. For a task tau I, how close is the performance of the merged LoRa L to the single task LoRa built just for that task? Let's call the metric for task tau I M tau I. We measure closeness with a ratio, the merged model score, M tau I of L divided by the single task LoRa score. When this ratio equals to 1, our merged model is as good as a dedicated single task LoRa. The aggregate score at step T is just the average of these ratios over all tasks seen so far. This formulation is particularly useful because it lets us combine completely different metrics which can have different ranges into a single score at each time step. For example, Rouge L for text summarization and tone adjustment, weighted rouge for smart reply, F1 for question answering, and F0.5 for grammar correction. Here we report performance at the final step. After all, 40 LoRa's have been merged, versus the storage budget K on x-axis, for two base models, Llama 3.2 1 billion and Qwen 2.5 1.5 billion. We show two references, zero shot, using no LoRa's, so the base model alone, and single task, where we keep all 40 separate adapters and pick the right one for each task. Importantly, all next methods share the same budget and the same similarity-based selection, only the merge operator changes. First, we show the main merging baselines, such as linear, ties, their ties. Then OPCM, a continual merging method designed and evaluated for image classification with fewer tasks. It doesn't transfer well to this setting. Finally, our two variants, K-merge and K-merge++, which robustly outperform the competing methods. To understand why this works, we analyze the cosine similarity of the trained LoRa's. We take all of them at once and compute the pairwise similarity between every pair. The matrix is organized by task. The first 8 rows and columns are the same problem type across the 8 languages. The next 8 are the second problem type, and so on. The clear pattern is the strong blocks on the diagonal. LoRa's cluster by problem type. On the other hand, similarity by language is weaker. We can also see that European languages are closer to each other than Asian ones. Inside each block, the dimmer subregions are exactly the comparison between European and Asian languages. The first 5 languages are European, the last 3 are Asian. However, this analysis is done after the fact. The system never sees all LoRa's at once. So, we run a controlled experiment. We fix the number of clusters to 5 and measure clustering consistency score. For each cluster, we take its most common task and check the fraction of LoRa's correctly grouped. K-merge++ reaches the highest consistency because it uses the remaining slots more meaningfully, and it's also more robust to adversarial task ordering. For more details, please refer to the paper and the code. Thank you for watching.